Hello and welcome to Elevate 24/7. This is Chetan Patel. In the previous set of videos, we have understood the concept of prime numbers, and we also understood that if a number is given to you, how you can identify that particular number is prime or not. And moreover, we also understood if a number is given to you, or maybe the limit is given to you, how you can generate the prime numbers up to that given limit. But when we're actually discussing these solutions, one thing we have noticed, like we are actually trying to write a very naive solution or very brute force solution. Let's say to identify this particular 7 as prime or not, I need to run a loop from 2 to 6. And every time I need to divide this 7 by 2 and 7 by 3 and 7 by 4, right? And I need to check whether the remainder is 0 or not. Okay. By chance, if the remainder is 0 and I cannot say this particular number which is given to me is prime, right? I can say it is not prime. Why? Because somewhere in this range, we have a number which is a factor of 7. So that's why if any one of the number is completely divided 7, we will get remainder as 0. And I can say that particular number is a factor of 7. So, and finally, I cannot say that this particular number is not a prime. Okay, so this is what I need to do. Essentially, to identify the number 7 as prime or not, I need to run 5 iterations, right? I need to run a loop for 5 times. It takes 5 iterations, right? And if I wanted to identify this 100 as prime or not, I need to run around 98 number of iterations. And if I wanted to identify this 1011 as prime or not, I need to run around 1009 number of iterations, right? So this is pretty expensive. Actually, it is going linearly, and at the same time, what is actually happening is unnecessarily we are running a loop for long time, which is actually inefficient. So now, can we optimize it? Yes, we can optimize it by using this very popular algorithm called Sieve of Eratosthenes. This is very popular algorithm, and what this algorithm will tell is, suppose to identify this particular 7 as prime or not, in brute force approach we need 5 iterations. But the Sieve of Eratosthenes algorithm will just take root integer of root 7 times. What does it mean? Which means that root 7 is somewhere close to 2.6. Integer of 2.6 is 2. It just takes 2 iterations to tell this particular 7 as prime or not. So essentially, to identify this 7 is prime or not, we are saving 3 iterations because it takes 2 iterations. But in brute force approach, it takes 5 iterations. And again, if I wanted to say this 100 as prime or not, in brute force approach I take 98 iterations, but in Sieve of if you do it with Sieve of Eratosthenes, it takes just 10 iterations, so that I can save around 88 iterations. So this is what Sieve of Eratosthenes will tell. So now we'll understand this particular algorithm very neatly. Okay, so this is an ancient algorithm, first of all. Okay, so we can use this for two purposes. First purpose is to find out all the prime numbers up to a given limit. We also can use the same algorithm to check the given number is prime or not. Okay, so this is what the benefit of the Sieve of Eratosthenes is. That's fine. Now we will try to understand the algorithm of Sieve of Eratosthenes. Yes. Okay, so let's have a look now. First, let's go to the first step of this. Okay, the first step is to understand the goal. Okay, what we need to understand here, this goal of this algorithm is to find out what all the prime numbers up to a certain limit. And first of all, what is limit? Suppose if I wanted to identify the prime numbers up to number 15, okay, I can say the limit as 15. Okay, this is what limit. Okay, hope you got my point. Fine. So now, before understanding this algorithm, I think it's better. Suppose if we, write the output before, because we can verify. So We know that the prime numbers up to 15, if I wanted to write, I can write 2, 3, 5, 7, right? And 9 can't be prime because it has a factor 3. 10 I can't write because it is having a factor 2 and 5, right? So I can write 11 and I can write 13. I can't write 15. Why? Because 15 has a factors 3 and 5, correct? So the prime numbers up to this particular up to this limit are 2, 3, 5, 7, 11, 13. So now let's verify how we can achieve the same output by using this Sieve of Eratosthenes algorithm. Okay, yeah, so let's get into the first, very, even though this is first step, and I think the algorithm step starts from step 2. Okay, the first step is to create a list of numbers. Okay, so we need to create a list of numbers. We'll see what numbers we need to list. Write down the numbers from 2 to the given limit. These are the numbers you will see. Okay, fine. So we need to write a numbers. Okay, from 2 to the given limit. Here the limit is what? 15. Okay, let's write the numbers from 2 to 15. Okay, we'll start from 2. Yes, we have now we have a row, the numbers from 2 to the given limit, which is 15 here, and these are the numbers that we are going to see. Okay, fine, that's fine. So next, let's get into the step number 3. The step number 3 is, let's start with the first number. Which is the first number here? 2 is the first number, right? So what we need to do, they are telling here, circle the first number, which is 2. I'll circle it, and what I need to do, I need to mark it as prime. I'll mark it as prime. Okay, the next, all the multiples of 2 greater than 2 can't be prime, so cross them out. The thing is, what are the multiples of 2? We know that the multiples of 2 are 2 ones are 2, 2 twos are 4, something like that. 2 threes are 6, like 2, 4, 6, 8, 10, 12, 14. Okay, these numbers, they are telling like they can't be prime. Okay, first circle the first number, which is 2, and mark it as prime. All the multiples of 2 greater than 2 can't be prime, so cross them out. Okay, we need to cross out all these multiples of 2, which is 4. Okay, so let's cross out this, and 6, 8, 10. Why we are cross outing? Okay, please try to understand, because 4 as a factor 2, 6 as a factor 2, so that's why we need to cross out that, because if they have because prime numbers are the numbers which are having factors only 1 and itself. Okay, if it is having any number as factors, then we cannot call that particular number as prime. Okay, we call that as composite number. So that's why we need to cross out all these multiples of 2, because these multiples of 2 are having a factor as 2 for it, so it will disobey the rule of prime number. So that's why we need to cross out all this number. So 12 and 14. So this is what we have done now. First, circle the first number, which is 2, and mark it as a prime. We marked out as prime, and we have crossed out all the multiples of 2, and we also understood that they can't be prime at all. Okay, that's fine. So now in the prime number list, what we have? We have 2 now. Now, next, let's move to the next step, which is step 4. What they are telling, move to the next uncircled number. Okay, so now we have circled this 2, which is uncircled number here. The next uncircled number, which is 3. Okay, so we are moving to it. Move to the next uncircled number, which is 3. Okay, and what they are telling, they are asking to circle it and mark it as prime. Okay, I am marking it as prime. Again, the same rule. Cross out its multiples. Okay, so cross out the multiples of 3 which are greater than 3. Okay, the greater than 3 are what? 6, 9, right? These are the multiples of 3. We need to cross out them. We have already crossed out 6, and we already crossed out this 9. We need to cross out now, and 12 is crossed out. 15 we are crossing out now. Okay, so now these numbers which are already crossed out can't be prime again. Okay, so next we need to repeat this step. Right, repeat the process, move to the next uncircled number. So now 2, 3 are circled, and the next uncircled number which is available to is 5. And what we need to do, we need to circle this particular 5, and we need to mark it as prime. And what we essentially need to do, we need to cross out, okay, all the multiples of 5. Okay, so 5 multiples which are available to us is 10 and 15, which are already crossed out. Please note that this point is very important, because when I come to 5, essentially I am there in third iteration. Please note this, I am there in third iteration. Okay, by the time I enter the third iteration, okay, what we essentially done, the multiples of 5, okay, are already crossed out by this previous numbers itself. Okay, that is what you need to identify, because this particular step is somewhere important. I'll tell you why. Okay, so now we crossed out all the numbers. Fine. So now we need to continue this process until you have circled and marked all the prime numbers and cross out their multiples. Okay, so now we need to do the same step, which is step 3. Essentially, you need to move to the next number, which should be encircled. Okay, so now this is the uncircled number 7. I will circle it and I will mark it as prime. And no doubt that 7 multiples which are available to me is 14, which is already crossed out again. Okay, that's great. And move to the next uncircled number, which is 11, and mark it as prime. And the multiples of 11 are not present, because the limit is itself up to 15, because we don't have any number. Like, next, move to the next uncircled number, which is 13, circle it and mark it as prime. So now, so we have done everything now. We have crossed out all the numbers and circled. So we have all these combinations, which means that we have traversed all the numbers from 2 to 15 now. Okay, now this iteration stuff done. Now the thing is, the prime numbers are 2, 3, 5, 7, 11, 13. So let's verify the same numbers again. See, this is what we have read before as well, right? So we have the same numbers, in fact, 2, 3, 5, 7, 11, 13. So essentially, what we have done over here, while identifying the prime numbers, okay, what we have done, we just run, 3 loops, right? So 3 iteration. Okay, by the time I am there at 5, okay, so I have identified all the prime numbers indirectly, correct? Because and after 5 I'm not crossed out any numbers at all. Okay, so everything is already crossed out. The remaining numbers which we have at that point of time, which are uncircled, is itself for the prime numbers. Okay, this is what we have understood. See, identity. Okay, so essentially we are taking very less iterations to identify all the prime numbers by using this sieve of Eratosthenes. Okay, to understand it more clearly, let's go with 7 now. Okay, we need to identify all the prime numbers up to this given limit, which is 7. Okay, how we can do it? So first we need to write a number from 2 to 7, right? 2, 3, 6, 7, right? That's great. So now what we need to do, first we need to circle the first number and we need to mark this as prime. Okay, next cross out all the multiples of this 2. Okay, so this is, I am telling, this is first iteration. Okay, fine. So I am cross out 4 and 6. Okay, so now I am moving to the second iteration. Okay, in the second iteration, move to the next number, next uncircled number, which is 3 here, and mark it as prime. And see, observe here. So now we need to cross out all the multiples of 3. So all the multiples of 3 which are present in this particular range is 6, right? So 6 is already crossed out. We don't need to check. We don't need to do. Okay, fine. So now the thing is, since we couldn't able to mark anything over here, 6. Okay, so we need to stop this. And remaining numbers which are present in this particular range of number are essentially prime. Okay, so we don't need to do anything. You just go and mark it as prime. You just go and mark it as prime. Okay, so essentially we just took 2 iterations, okay, to cross out all the non-prime numbers, and the remaining numbers which we left should be prime. Okay, this is what we have done. Okay, so now we took 2 iterations. Okay, so now we can write a code for it. Like, suppose if you wanted to identify the prime numbers up to the 7, how many iterations you just need? Root 7 of int. Okay, root 7 of int is nothing but int of root 7 is 2.6. Int of 2.6 is essentially 2. You just need 2 iterations. But before, if you wanted to identify this 7 as prime, you need to divide this by 7 and you need to compute the remainder. Okay, you need to go with 3 again and you need to divide this with 7. Okay, you just need to compute the remainder every time, right? You need to take 7 percentage 4, right? So 7 percentage 4 is 3, and you need to go 7 percentage 5, which is 5 ones are 5, you are getting 2 as a reminder. Okay, so every time you need to check with every numbers, right? You need to take this 7 percentage 6 and here the 1. Correct, right? So in total you run the iteration from like 7 percentage 2, 7 percentage 3, 7 percentage 2, 2 3 is a 6, and 1 you are getting as a reminder. Okay, 3 2s are 6, and your 1 you are getting as reminder again. So which means that you just write 5 iterations, but here just 2 iterations are enough. Suppose, for again, if you wanted to identify this 100 as prime or not, okay, you just need 10 iterations to identify the given number as prime or not, or to generate all the numbers up to that limit. So that's why Sieve of Eratosthenes is something which will help you, to write an efficient, solution. Okay, when you are actually working with a prime, because there are some instances when you are actually coding, you need to use the concept of this prime number, or you might need to generate a pattern, okay, that follows this prime number. Okay, so that's why it's very good, okay, if you would have learned this mathematical algorithm, okay, which help you to write an efficient code, which give the strong foundation in mathematics while writing a code by writing an efficient solution. So hope you guys understood this particular algorithm neatly from very scratch, and we have also understood why the brute force solution is not efficient. Because if you wanted to identify any number n as prime number, you need to run n minus 2 iterations. Okay, and if you wanted to identify uh, with this brute force approach, okay, right, if you wanted to identify this n as prime or not, okay, you just need to write root n of int. Okay, which means that you need to write the integer of root n, okay, times, which is essentially very less compared to this n minus 2, right? N minus 2, which is very big compared to the int of root n. Okay, so this is how I can write this in mathematically. Fine. So thank you for watching this. I hope this video is, very important and very crucial, and I hope you guys are happy with this algorithm. Meet you in the next video. Please don't forget to subscribe and like button. Hit the like button. I'm very grateful if you do so. Thank you so much.